Hi, my name is Dan Gilstrom. I'm presenting 10 things computer scientists should know about the power grid. Well, it's actually now 11 things. I started with 10 and then felt compelled to add an 11th. This presentation is targeted for computer scientists learning about the electric power grid. So the topics discussed here are drawn from my experience as a computer scientist learning how the power grid works. So learning about any complex system for the first time can be intimidating, and the power grid is no different. So let's try to abstract away some of the complexity and, when possible, try to reframe some of the key challenges faced by the power grid to problems that use computer science terminology, which we're more familiar with. Okay, so the first topic that confused me and it took a while for me to really get clear was at the very basic level, what's the difference between energy and power? Especially since the two terms seem to be interchangeably quite often. So energy is simply the amount of work that can be done by a force. Put differently, it is power without the element of time. So power, on the other hand, is the amount of energy required per unit of time. That is, the rate energy is transmitted or used. So to summarize, energy does not consider time, while power is energy as a function of time. So at the most basic level, the job of the electric power grid is simple. It's to generate electricity at the moment that is demanded. In other words, the power grid must balance the supply and demand of power in real time. So as we'll talk about later, energy storage in the power grid is minimal, so this delicate balance must be managed instantaneously. So in stark contrast to the operating environments in goals that we are accustomed to as computer scientists, so for example in the internet in particular, reliability in the power grid is the number one concern. So here reliability means safe operation of the power grid with nearly no downtime. So currently in the North American power grid is available 99.9% of the time. So this means 8 hours of outages per year, where in practice most of those outages occur at the sub-second time scale, which humans can't actually perceive. So as a result, nearly every problem we talk about in this course will consider reliability before any other constraints are optimized. So in fact, actually one of the primary motivations for the smart grid is to increase the reliability of the power grid through, among other things, better instrumentation and measurements using devices like PMUs that we've talked about so far in the course. Okay, so the third topic that I picked out was it concerns the structure of the power grid. So the power grid divides into three subsystems. So one, power generation. Two, transmission, where the transmission network handles bulk transfer of electrical energy, sending high voltage electricity from power plants over long distances to distribution networks, which make up the third major part of the grid. So each distribution network consists of lower voltage power lines, and these distribution networks deliver power to homes, businesses, and other end consumers. So the transmission network can be thought of as the backbone of the power grid and typically has a mesh-like graph structure. In contrast, the distribution network has a hierarchical structure and for cost reason typically has a tree-like structure. So the excuse me. Lastly, taken as a whole, the traditional model of the power grid is centralized generation of power that flows one way from producers to consumers. So this power distribution paradigm is shifting with the advent of distributed power generation, like distributed power generation sources like wind and solar. So again, to reiterate, power historically is generated centrally and is pushed out as a one-way flow from producers to consumers, as shown here by the black edges. Okay, let's look at the same diagram but from a different perspective. So we can define a power grid as consisting of a set of buses, where a bus is either a power generation center, electrical substation, or an aggregation point of electrical loads. And connecting these buses are electric power lines. So in more familiar terminology, a bus can be thought of as a node in the graph, and the power lines can be thought of as links connecting those nodes. Okay, so number 4, the power grid is operated and managed at different time scales. So recall, the central goal of the power grid is to balance supply and demand at every time instance. So this balancing act takes place at different time scales. So at the sub-second granularity, the main concern is frequency regulation. So that is generating power with the correct frequency and phase. At the minute time scale, operators are concerned with balancing supply and demand in real time. For power grid operators, this may involve increasing power generation on the supply side or shedding load on the demand side. So this, as it exists today, is a partially automated process. So some generators can be signaled so as to increase or decrease output in an automated fashion. And more manually, operators may actually place phone calls to ask large energy consumers to reduce their load. At a timescale of hours and days, the primary concern of operators is to optimize which generation units should be used and at what power level in order to meet predicted demand while minimizing overall cost. So this is actually a really interesting and rich optimization problem, as it involves two types of prediction: forecasting future load and predicting energy prices. So lastly, at the timescale of weeks, months, and years, the primary concern is to, one, predict how power demand will both increase locally and system-wide, and two, to use these estimates to accommodate growth with the appropriate upgrades in transmission and distribution hardware, and possibly even constructing new generation units. Okay, so number 5, currently energy storage in the power grid is minimal. So in his 2010 TED Talk, Bill Gates said that if we take all the batteries that get made from cars, computers, etc., and compare this with the amount of electrical energy the world uses, that all these batteries we make could store less than 10 minutes of all the world's energy. So I believe if large-scale energy storage were possible, it would change the entire landscape of the power grid, allowing most significantly for power generation to be decoupled from its consumption. So for example, we could capture energy produced by intermittent sources like wind, store it, and then consume it the next day when energy demand is higher or prices are higher. So my opinion is that the technical and economic push factors are finally here to encourage people to solve this energy storage problem. That is, to hopefully greatly increase the amount of energy storage available in the power grid. So one important aspect of power generation consumption that long confused me is that power can't be routed. So at every instant, power is generated to meet the instantaneous demand. For each power generation site, the power flows out along all connecting paths to the power consumers as dictated by physical laws. So I tend to think of power generation as being dumped in a shared pool, and the energy consumers simply pull the energy out that they want. So under this model, a consumer can't actually select the power source it wants to receive energy from. So as pointed out by S. Keshev's excellent Google Tech Talk called How the Internet Can Green the Grid, the power grid is grossly inefficient. So for example, in Massachusetts, 15% of the generating capacity is needed fewer than 88 hours per year. And this is largely as the result of building what are called peaking plants, which are essentially turned on only during the hottest days of the year, which are used to supplement the daily baseline power generated to meet the peak demand on those days. So as this quote shows, that very often these very expensive power plants are not used through through a large part of the year. So as an aside, I think one of the most interesting topics in smart grid research is an area called demand response, which instead of looking at how to increase power generation on the supply side, it looks at how to incentivize consumers to curtail or lower their power demand during times of peak demand. So I believe some of these topics are actually later covered in this course. So from the same talk by Keshav, he provides what I think is a really nice analogy which links the power grid and computer networks. So he states that a power grid is like a content distribution network that has no storage buffer and must produce and deliver content for a single content stream. So I've mentioned several times that the key challenge of the power grid is to generate power at each instant it is demanded. So you might wonder how can this be done when the consumer load profiles are variable? So this problem of scheduling power generation becomes tractable through the use of statistical multiplexing or aggregation, along with the fact that energy demand is quite periodic as a function of the time of day. So in this generic example shown here at the bottom, we show the energy consumption as a function of the time of day. So we have the individual load consumption profiles on the left and the resulting aggregated consumption profile on the right. So on the left are shown several variable energy consumption profiles, which you can think of as the demand of an individual home within a neighborhood. That is, each curve corresponds to a home, and the aggregate profile on the right would correspond to the aggregate demand of that neighborhood. So this generic example shows, or should hopefully give you the idea that statistical multiplexing derived by aggregating loads makes planning of power generation from the supply side much easier than it would be if you considered each of these homes individually. Okay, so the final point is that the power grid as it exists today is outdated and essentially has not undergone any significant changes since the 1960s. As has been discussed by previous presenters, the power grid is operated very conservatively, which can both be very wasteful and also problematic in terms of its reliability. So we saw that in the July 2012 India blackout. So for me, I think the good news is that this leaves many interesting and important problems for researchers and practitioners alike to tackle. So many of these topics, as I understand, will be covered in this course. Okay, so this concludes the major part of the presentation. Additionally, I just wanted to share with you some additional resources which I found useful. So first is the Google Tech Talk done by Keshav that I alluded to earlier in my presentation called How the Internet Can Green the Electrical Grid. So there's also a corresponding CCR paper that has the same title. The textbook by Alexandra von Meyer gives a very thorough description of the nuts and bolts of the power grid and is an excellent resource. And finally, David McKay, who's a physics researcher, professor, has a free online textbook called Without the Hot Air that addresses sustainable energy and provides a really thorough analysis of what it would actually take to have an entire nation, in his case he considers the UK, to run completely on sustainable energy. And there's actually a very nice 10-page summary of the book, which essentially covers mostly everything you want to know. So I want to thank you for your time and hopefully attention. And if you have any questions, feel free to email me, Dan Gilstrom, at the email address shown here. And again, thank you.